are moving, is it possible for us to stop them? So the material that we can use to stop this energy will also vary depending on the type of radiation that is emitted. If we say we are not going to stop it, can it stop on its own? Yes. How far will it go? What will be the range in air? I'll give you an example of a bullet. When you fire a bullet from a gun, in the movies, we see people catching bullets, but even if we don't catch them, there will be a point when they will land on the ground. The range, of course, must be talked about. Mother, stop that. Right here. Right here. Stop writing on your hand. Right here. Yeah. Then the other thing is, what causes an object to have a specific range? Because when you throw it upwardly, it will be able to land on the ground. Now, if we don't want to stop it, we just want to distract it. Maybe we are going to bring in, though the other point is not even here. We are going to bring in a magnet. Can a magnet affect how these particles will move? What about the electric charge? Does it also affect? Yeah. Therefore,
Okay.
because of the electric charge, and we understand that electric terminals, one is positive, stop that you. One is positive, the other one is negative. Therefore, we should be able to discuss their charges. These particles that come from an atom, are they charged? What are their overall charges? And then the last one is for it to be a charge, or second last, for it to be a charge, meaning it is able to ionize. How strong are their ability to ionize? Then the last one, of course, is the penetration power. Now, the penetration power depends on the range in air. If something has a short range in air, we expect it not to penetrate through something that is strong, right? Look at a bullet gun. Or a bullet rather. When you fire a bullet, because it is able to go a very long distance, that's why if even its penetration power is actually very strong, very high. But when you throw a stone which can't go very far in air, you realize that even the material that you can use to stop it is very small, one. Two, even the penetration power is very weak because that object cannot go very far in air. But I said stop. Miss, do you understand?
Yes, sir.
That's a connection. So when you compare a stone from your hands and from a catapult, the one in a catapult will go a longer distance, and we expect to have a long range, and its penetration power is actually very high. Yeah. So those are the. But maybe the other thing that we have to talk about is how does the mass affect? If I gave you 2 kg sugar, I ask you to throw it with your hands, and then I've also given you 2 blocks. I ask you to throw those blocks. Which one do you think will go a longer distance?
The sugar.
Because the mass is smaller, right?
Yes.
So all these properties that you are seeing here are actually connected in one way or the other. Once you understand one, believe you me, you'll be able to tell all of them because these properties are actually connected.
Okay.
Sit and write. Stop writing. I gave you here. Sit and okay. So if that is clear, we can now move on to the actual table. So the actual table, the one now that will guide us. Where is the table actually? Uh-oh, I don't even have it. I'm sure I'll find it. I will find that table. Oh, I think it's at the end. Okay. Now let's look at one after the other. One after. Let's look at alpha, beta, and gamma in terms of the nature and the charge. Alpha, the nature and the charge are somehow connected. Say alpha, the nature, 2 protons and 2 neutrons. What does it mean? It means when we have an atom, remember 2 protons and 2 neutrons gives us the mass number, right?
Yes, sir.
Exactly. And remember the protons gives us the atomic number. So if we have an atom Z, okay, let me say atom P, we have atom P whose mass number is A and atomic number is Z. When it breaks down, we will have another element O plus another one where from this parent, the 4 will be subtracted because the combination of these two give us the mass number. And the protons will give us 2 as the atomic number. So meaning each atom that we have, which emits alpha particle, we expect the mass number to reduce by 4, and we expect the atomic number to reduce by 2. Because at the end of the day, the combination of these two should be able to give us what we started with. So that is the meaning of alpha particle and its nature. That is what it actually means. Now, let's look at proton. Let's look at neutrons. What are they? What is the charge of a neutron? What is the charge of a neutron?
I'm not sure.
Ah, Mercy, you should know. The neutron actually has no charge. That's why we call it neutral, because it does not have a charge. Right? So in terms of the charge, the neutron has no charge. What about a proton? Each proton has a charge of positive. Now, because protons are 2, how many charges will be there?
2 positive charges.
That's where the charge is coming from, as a positive of 2. Very important. And this is the only point where all other properties actually are based. Once you understand here, believe you me, everywhere you will go, you will realize that we're all coming back to this. Yeah. What about beta? Beta, each time an element emits beta particles, the atomic number increases by 1, The atomic number increases by 1. Yeah. The atomic number increases by 1, the mass number remains the way it is. I will explain. However, what causes the increase in the atomic number is because of the addition of one electron, the one we are calling a fast-moving electron. So the addition of one electron increases the atomic number. I will explain.
Okay.
For gamma, the atomic number does not change. The mass number does not change. It remains the way it is, but actually a lot of energy is emitted. I will also explain. However,
Okay, sir.
part where we are saying ionization effect, if I made a mistake, this here is supposed to be the charge. Supposed to be. So that's why we are saying the charge for alpha is 2 positive. The charge for beta, because there's a fast moving electron, each electron comes with its own negative charge. That's why we have that single negative charge here. And gamma, because nothing changes from the atomic number and the mass number, therefore it has no charge.
Okay.
Please ask me or
Sir, I have a question actually.
yeah.
Can you give examples of these same alpha, beta, and gamma for each of them?
Yes, actually, yes, but this is just the introduction. I'm just introducing. But if you've already learned and you already have ideas, I can skip the rest and go direct to the equation.
Yes.
You have learned them.
Yes.
Well, then I'll just run it through. Let's see the next page. The next page here is the next page is just talking about the approximate mass. You understand?
No.
Okay. So, like, remember what I told you? What I told you was this. I told you was two protons, and 2 electrons. They'll give us the mass number. So 2 plus 2,
Mm-hmm.
2 plus 2.
4.
That's why
4.
that's why we are saying the mass for alpha is 4. What about beta? What did we say? It's a fast-moving electron. And what is the mass of an electron? Sometimes they just tell us it's negligible.
Okay.
What about gamma? Nothing changes, therefore it has no mass. The mass is 0.
Okay.
So it's at this point here I said combining of 2 protons and 2 neutrons is actually what is giving us a mass of 4.
So what does AMU stand for?
Atomic mass unit. They tell us that the mass number is measured in grams, but some books they tell you that it's atomic mass unit because there are a lot of other units that are actually used.
Okay.
Yeah. The next one is this one. Are we okay with it?
Mm-hmm.
Okay. That one stopped by are we good?
Mm-mm.
Okay. Because alpha, remember what I told you about you being given 2 blocks and having sugar, 2 block sugar will go a longer way because it's lighter. So because alpha is the heaviest, it can easily be stopped by what? a single paper. Well, because the range is very short, it doesn't go far due to its mass. The good example I'll give you is when you have a remote controller, you put a paper between the remote and the TV. Will the TV respond?
No, it won't.
You put especially a very thick paper, it won't, meaning the rays or the energy that's coming from the remote has been stopped because those don't go very far. But Bluetooth, which goes a bit far, even if you hide the microphone in the paper, you wrap it around, you find that when you speak, sound will be able to be detected even by the speaker because those can go a longer distance in air. That's why even the material that is stopping them is not a paper. So when we go now to a beta particle, because the beta particle is only an electron whose mass is slightly smaller than alpha, we expect them to pass through the paper, but aluminium is actually able to stop them.
Okay.
Then
Can
for
you give an example?
what?
Can you give an example
Example.
for beta?
What do you mean the example for beta?
So, like the way you gave an example in alpha for the microphone or
No,
the
no, no,
remote.
no, 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 no. Those are actually not even example. Those are not the actual elements. I was just giving an example of what actually happens.
Oh, okay.
But the one that has got a higher penetration power, according to those three that we have, is gamma ray, and we are saying they can be stopped by lead.
Okay.
But even when we say this, there are other rays that are very strong, like X-ray. Remember, X-ray can pass through any human being, no matter how fat they are. Remember when you go to take an X-ray photography by a radiographer, it will pass through, and on the shadow of the bones are the ones that are captured on the photograph. So meaning they have got a very, very, very strong penetration power. So all those are dependent on the nature of alpha particles. Yeah. That's what this page is all about. How okay are you with this one?
I'm fine, sir.
Okay, this one I need to explain. I need to come back and explain on the deflection by reductive. Even this one, I need to come and explain. But now let me show you. So this is a summary of the table. I'm sure I should have seen it. So because the nature of alpha is 2 protons, 2 electrons. When we add them, we'll have the mass of 4. Go to my okay. Yeah, among others which this table can be sent, but I want to show you the examples of actually what happens. But sometimes they will ask for the uses. Where do you think we use alpha particles? So alpha is used in smoke detectors. Have you ever watched the movie called Enemy of the State?
No.
Mwetambuka na movies wenotukwatamba fyama amaziwa odipi yabutefyekafyeka. So in the movie Enemy of the State, there was Will Smith, that guy who was being followed. So what he did, okay, let me not go very far. In banks, they don't allow fire. In banks, they don't allow guns. It is because in banks, they have put these which are called smoke detectors. You'll understand with me that you might have watched certain videos. The moment fire or heat just is detected, you will hear the siren ringing, even water start coming from the roof. I'll share with you a video from some of the sources. So in big places, even Palevi actually, Levy Park Mall, though they have closed it, they have got smoked, not Levy, Society Business Park. There are detectors there. You just enter, you're going to see, it looks like it was small ventilators, round ones. Those actually contain water. Meaning the moment heat is detected within the building, they have got drums on top, then they'll start more or less like artificial rain. Meaning even if you're not in your room, mess, some fire breaks out. Once the smoke is just detected in your room, water starts falling from the roof in order to put off the fire.
Okay.
Those are smoke detectors, and we use alpha. The second one is in treatment of cancer, though sometimes the treatment of cancer is partially used for beta, but for beta we are saying the cancer that it treats is the eye and the bone. Here they specify. Here they just say cancer. Skin cancer actually. Why skin cancer? Because these guys have got short range. So if you subject them to the body, they can only end up the skin. Remember, they're being stopped by the paper. So meaning only those cells that are in the cancerous cells that are in the skin can be treated. The bones, remember, the bones are underneath. We have got the skin, we have got the flesh, and then we've got the bones. So the only ones that can go all the way up to the bones, we need those ones that have got a better penetration power. Yeah. Then gamma say they are used to sterilize surgical equipment. I don't know how I would say this, but do you know surgical blades?
Yes, sir.
Those surgical blades, I wanted to get one. Those surgical blades are actually sterilized by gamma rays. If only I could be allowed to put up my to turn on my camera, I should be able to show you something. I should be able to take it. Uh-oh. Should be able. Should be able to actually show. Okay. I'm gonna just turn on the light. You seen these, huh?
Yes, sir.
So these surgical blades, it's just that maybe it's in the night. Somewhere here, if you were to read, let me see if you can. I don't know if you are able to see. Somewhere here,
Yep.
there's somewhere here where
Okay.
above here, it is said sterilized by gamma rays. Yeah. So when they use the word sterilization, they're actually talking about the process of making sure that the instrument that we are using does not contain any bacteria. In case the moment you're operating on a wound and then that instrument contains the bacteria, you find that you might end up infecting the wound. So they have to make sure that all the bacteria are removed, and the process is called sterilization. And once the bacteria sit on food, they will actually facilitate the rotting process. Therefore, once we express or once we subject our food and fruits to gamma radiations, all the bacteria will actually die. By so doing, what are we doing? We are preserving or we are prolonging the food. Yeah, so that's why the other point said it is used to prolong the food, and yeah, it's used to prolong the food, but we can also say preservation of the food. Okay. Now this one is different. Now let me show you how actually questions come in an exam to do with the decay curves, right?
Okay.
The decay curves. I hope I find it fast because got no time. Now this is physics, senior physics, past paper, not physics but science paper 1. Okay, I will find it. Then you will be able to see. I will find it and you will be able to see. I didn't know we could reach here, so I didn't really go further in my presentations. Look at this question that came in 2016. The question says lanthanum with atomic number 57, mass number 139, emits an alpha particle to form cesium, followed by an emission of beta particle form barium. Express these changes using nuclear equations. Very important. Very, very, very important. I want you to pay attention to what we are actually going to do. So we will first write the element which is emitting, which is lanthanum. It's La with mass number 139 and atomic number 57. Are you seeing?
Yes, sir.
So this element undergoes alpha particle emission. They've told us that what we are forming is cesium. How do you write the decay curve? By alpha emission, I said from the mass number, what are we getting? My student, from the mass number, how much are we getting?
From the mass number, we are getting 139.
From 139, how much are we subtracting?
Oh, 4.
Exactly. So 2 protons and 2 electrons is giving us 4. So when we subtract 4 from 139, what are we getting? 135, right?
Yes, sir.
From the atomic number, how much are we subtracting?
2.
Plus C, 4 here, 2 here. Now the only element that has such kind of combination is the helium. Then if you want to even indicate energy to show that a lot of energy was actually produced. But sometimes, instead of having all this, we can just put up the symbol for alpha. It is all good. But they've told us followed by So the same cesium underwent beta particle. They've told us that what was formed was actually barium. So we are going to start with the same cesium. Because when you start something, you end it on the way. The other person will also have to start from where you left it. So this is 135. And then 55. What did we say about beta particle?
We said that we subtract it by 1.
Actually, no. I said the mass number increases.
Oh.
So from 55, we are going to have 50.
6.
But the mass number remains unchanged. Plus, here you can either use a symbol for beta or you can use a symbol for an electron. If you so wish, you also indicate plus energy. Are you getting something?
Yes, sir.
Yeah, that's it. That's it. That's it. So that's how questions comes. Have you taken note of that?
Mm-hmm.
Let's look for another one. Let's look for another one. Let's look for another one and see how best we can solve it. Mostly such questions come section A, the last part, the last question. So this one, that's where it's coming from. This one, that's where it's also coming from. And unfortunately, there are things that we have not learned, so I may not talk about them. But are you getting something, by the way?
Yes, sir.
Okay, another one here says an element X with atomic number 117, mass number, atomic number 58, emits an alpha particle to form element Z. One says, what's an alpha particle? So alpha particle, when they say define an alpha particle, you are only supposed to talk about its nature. So you say that this is a particle that has 2 protons and what?
2 and then 4 and 2. Yes, sir.
Don't bite your tongue, my dear. 2 protons and 2 neutrons. As simple as that. 2 says write the decay equation which represents these emissions. So you're gonna write as X the starting element, which is called the parent. We put up an arrow. We are using the symbols they have told us. What was formed was Z. It's alpha. On top, we're going to subtract a 4. We'll have 1, 1, 3. 1, 1, 3. Then from the 58, how much are we subtracting?
2.
And what are we remaining with?
56.
Exactly. So that is what actually happens. 56. Plus, the something I said, you either put helium or you can just put alpha. It's all good. It's entirely up to you to decide which one works best for you.
Okay, sir.
Otherwise, we can end here today. I don't know if there's anything you've learned. And what do you have any question?
If there's anything,
What?
no.
Okay. Thanks. Good night.
No, sir, I don't have a question. Good night, sir.
Boom, boom.